nearly 3,000 tons of explosives, 17 years of drilling, 140 meters beneath the ocean floor. That is what it took to carve Japan's Seikan Tunnel, 53.85 kilometers of railway passage buried under the sea. It stands as one of the greatest feats of underwater engineering ever attempted. But why do nations risk billions building beneath the ocean? And how is a radically new construction method about to change everything? When a country decides to dig beneath the sea, it is rarely just about beating a record or chasing prestige. The stakes are national, sometimes existential. Islands and peninsulas, cut off by nature, face harsh weather, unpredictable seas, and the constant risk of isolation. Ferries can be halted by storms or ice, while circuitous land routes cost time and money. Permanent undersea corridors promise a different future, unbroken lines of trade, year-round mobility, and a direct link between regions that once felt worlds apart. The promise of these tunnels is as much about resilience as it is about speed. A fixed link can keep cargo and people moving when typhoons, blizzards, or high winds shut down everything above water. For countries like Japan, Denmark, and Germany, the ability to guarantee movement no matter the weather translates to economic security and regional integration. Factories on one side of a strait can supply markets on the other without delay. Businesses can plan just-in-time shipments with confidence. Commuters and travelers are no longer at the mercy of the sea, but the impact goes beyond economics. Undersea tunnels also offer a path toward cleaner transport. Electrified rail lines running beneath the ocean can draw travelers and freight away from carbon-heavy ferries and short-haul flights. That modal shift cuts emissions, especially as more renewable energy feeds national grids. For governments, the decision to invest billions in these projects is a bet on the future. A wager that the benefits of seamless, low-carbon mobility will outweigh the immense technical risk and cost. It is this mix of ambition, necessity, and environmental urgency that drives nations to attempt what once seemed impossible, forging permanent arteries under the sea where only the boldest engineering will do. Beneath the churning waters of Japan's Tsugaru Strait, the Seikan Tunnel stretches for 53.85 kilometers, making it the world's longest railway tunnel. Of that distance, 23.3 kilometers run directly under the seabed, buried as deep as 140 meters below the ocean floor. The sheer depth and length demanded engineering on a scale rarely attempted before. Construction began in 1970, and it would take nearly 2 decades, 17 years of relentless excavation, blasting, and reinforcement before the tunnel opened in 1988. The project pushed the limits of what was thought possible. About 2,900 tons of explosives carved twin bores through ancient rock, while nearly 168,000 tons of structural steel formed the backbone of the tunnel's lining and support systems. Every meter gained was hard-won, with crews battling not just the geology, but the constant threat of water intrusion and seismic activity. The chief tunnel engineer and his team worked around the clock, adapting to shifting ground and pressure spikes that could flood a chamber in minutes. To handle both high-speed Shinkansen and conventional trains, the Seikan Tunnel introduced a triple slab track system, a rare design where 3 continuous concrete slabs support the rails, reducing vibration and allowing for precise alignment even at depth. Safety was a constant concern. 2 large emergency stations were built deep inside the tunnel, later converted into museums that now display the tools, plans, and personal stories of those who made the crossing possible. Seikan stands as a benchmark for undersea tunnel construction, a feat of endurance, ingenuity, and exacting detail. Its lessons and records would shape every deep-water tunnel that followed, setting the bar for what the next generation of engineers would attempt. 18 kilometers of the Baltic separate Denmark and Germany, but the Fehmarnbelt Tunnel will erase that distance in a way no deep-bored tunnel ever could. Instead of carving through bedrock, engineers are assembling the world's longest immersed tube, an underwater puzzle built from 89 massive concrete elements, each nearly the length of 2 football fields, plus 10 special sections for power and ventilation. At the heart of this operation is a casting yard on Lolland, a sprawling industrial zone where 6 production lines work in parallel. Every few weeks, another 73,000-ton segment rolls out, measured to within a centimeter. Precision leaves no margin for error when these giants must lock together on the seafloor. The journey from land to seabed is a feat of coordination. Each element is floated out on a custom immersion pontoon, its ballast tanks adjusted to keep it neutrally buoyant. Winches and steel cables, stretching up to 23 kilometers, maneuver the segment into position above a trench dredged into the seabed. Draft sensors and GPS data feed into a control algorithm, guiding the descent at just 10 centimeters per second. The final placement must land within 5 centimeters of the target, and hydraulic jacks make the last delicate adjustments. Once in place, divers and robotic systems seal the joints with rubber gaskets and stainless steel rings, then pour a concrete sleeve to lock everything watertight. The payoff for this industrial choreography is speed and reliability. Where ferries once took 45 minutes, cars will cross in 10 minutes, trains in just 7 minutes. Rail will run at 200 kilometers per hour, road traffic at 110 kilometers per hour. The head of element production calls it assembly line infrastructure, a project where precision and repetition replace the slow grind of deep excavation. For travelers and freight, the result will be a seamless, weatherproof link built not by tunneling under the sea, but by assembling the sea's own bridge just out of sight. A tunnel beneath the Baltic is not just an engineering challenge. It is a financial and environmental test. The Fehmarnbelt project comes with a price tag of 7.4 billion euros, a sum scrutinized by government auditors and the public alike. Every euro spent must deliver not just a faster crossing, but a cleaner one. That is why the team's approach to sustainability is woven into nearly every stage of construction. On the casting lines in Lolland, the concrete recipe itself has changed. About 30% of the traditional cement is replaced with fly ash, a byproduct from power stations that would otherwise be waste. This low-carbon mix cuts the tunnel's embodied emissions by nearly a third compared to standard concrete. Over the full 400,000 cubic meters poured, that means thousands of tons of carbon dioxide never enter the atmosphere. The project's sustainability manager describes it as a quiet revolution, one that does not slow production, but fundamentally changes what is possible for megaprojects. Electricity is another battleground. Instead of relying solely on Denmark's national grid, the tunnel's construction sites are powered in large part by offshore wind farms. At peak, up to 80% of the electricity used to drive cranes, pumps, and casting machines comes from renewable sources. The same commitment extends to tunnel operations after opening. The ventilation and lighting systems will draw from a grid where wind and solar make up a growing share, pushing the project toward carbon neutrality over its lifespan. The opening target is mid-2029. By then, the Fehmarnbelt will stand not only as the world's longest immersed tube, but also as a benchmark for how infrastructure can shrink its carbon footprint without sacrificing speed or reliability. For Denmark and Germany, it is a test case. Can a megaproject deliver on both climate promises and economic discipline? The answer will echo far beyond the Baltic. Every tunnel beneath the sea is a contest with the unknown, and nowhere is this more apparent than in the way engineers confront risk. Beneath the Tsugaru Strait, Seikan's deep-bored lining faces pressures up to 1.4 megapascals, roughly 14 times the force of a car tire, while the Fehmarnbelt's immersed concrete shells contend with the shifting sands and currents of the Baltic. Both rely on a design safety factor, gamma E, of 1.5. Every calculation for water pressure and material strength is multiplied by this margin, forcing the structure to withstand loads far beyond the worst-case scenario. Seikan's chief safety engineer describes the tunnel as a fortress, its triple-layered lining and real-time sensors built for earthquakes and sudden surges. In the Fehmarnbelt, redundancy is woven into the very joints. Rubber gaskets compress under hydraulic force, and every element is backed by a secondary seal. Ventilation, too, is double-layered. Forced air systems and backup fans stand ready for fire or blackout. The logic is simple but unforgiving. One failure must never bring the whole system down. This is the partial factor approach, a philosophy as much as a formula, now written into codes from Tokyo to Copenhagen. The Channel Tunnel, linking the United Kingdom and France, takes a different approach. It is a 50.45 kilometer twin-bore rail tunnel with 37.9 kilometers running below the English Channel. Here, engineers relied on deep bored excavation through chalk marl, creating parallel tubes and a central service tunnel for safety and maintenance. In contrast, the Hong Kong-Zhuhai-Macau Bridge features a 7-kilometer immersed tube assembled from giant concrete segments and laid across the seabed to connect 3 cities in the Pearl River Delta. Each project answers the challenge of crossing water with its own blend of technology and risk management, whether boring through rock at depth or assembling watertight segments in shifting currents. Together, these tunnels show that there is no single blueprint. The world's longest undersea links are shaped by geology, traffic needs, and the ambitions of the nations that build them. Beneath over 100 meters of ocean, steel and concrete defy the planet's most relentless pressures. As nations push for faster, greener connections, each tunnel, from Seikan's 53.85 kilometers to Fehmarnbelt's 89 prefabricated sections, shows what is possible when ambition meets engineering. The next frontier isn't distance, it's depth. What challenge comes next?